Today we're going to go over lesson 37, the proportion of orange Reese's Pieces. So there is a website you need to go to, if you can get there, for doing this, and let me show you that right now. It's in the description on Google Classroom. Rossmann and Chance are the names of two statisticians. What a name! Chance for a statistician. Fantastic. Well, they created this app so that we wouldn't have to do the simulation. In the lesson it says the proportion of orange is going to be 40%, so I've set it up to be 0.4 over here in the upper left hand corner, and the number of candies is 50, so the sample size is 50. It says, suppose a large bag of Reese's Pieces has 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? And the random variable is the number of orange candies in the sample. Well, let's just see what happens when we go ahead and play with this app. We're going to go ahead and draw samples. So there's our estimation of 50. After you do this once or twice, you're going to want to turn off the animation. Okay, so even though the proportion is supposed to be 40%, it says here we got 16 orange ones. That is 32%. So just like when we did our project on simulation, we may aim for one thing, but we may get a completely different number. And that's the variation that comes from sampling. Well, let's look at, see if our stream is still... Okay, number one, what type of probability distribution does X have? Justify. Well, if you think about it, they're either orange or not orange. We are not replacing the Reese's Pieces, so it's not really independent, but since there's 1,000 pieces, we're not taking more than 10% of them. 10% of them would be 100. So since the sample size is 50, we're okay that way. The number of trials is fixed. It's 50 candies, and the probability of success remains the same throughout. So it looks like we have binomial because we have B, orange or not. We have I. In this case, it's not technically independent, but the 10% rule says that 50 is less than 1/10 of 1,000 because there's 1,000 pieces. N is fixed at 50. 50 candies. And S, which is probability of success, remains constant at 0.5. Nope, sorry, 0.4. Any questions so far? Let's see. So there's what I have for number one. It's basically what we were doing in the last unit with bins. We're trying to figure out, you know, what is it exactly. Okay, number two would be something that we would do as a class. It says draw a sample of 50 Reese's Pieces using the applet. How many pieces were orange? And repeat this 5 times, writing your values below. So that would be something each individual person would do. Probably would have the Chromebooks out at this point. And then number 3, write the values on sticker dots and add it to the dot plot on the board. Well, this is usually where I go through the class and I ask each of you what your data was, or I ask you to come up to the board and write your own data on the board. Well, obviously we can't do that in this situation, but we can go back to the app. Okay, so what we'll do here is, if you notice, we can change the number of samples. So assuming there's, uh-oh, my keyboard won't come up. Let's go to 150 and draw the samples. Okay, much better. Now, I'll give you a little preview. Here's kind of what we're after here. You see over on the left side it says normal approximation. If you go ahead and click that, overlays the normal curve. Do you see how normal these dots became? I mean, they're not great, right? But here would be the exact if it was a binomial. So not very different. That's sort of what we're after. So each dot is going to represent the number of orange from a sample of 50. The number of orange from a sample of 50. Now that would mean that the scale here, okay, what would be our expected value? Well, if you think about it, if we have 40% and we took 50 at a time, we would expect the mean to be 20. So our peak should be 20. Okay, so what is the mean and standard deviation for the distribution of x? Well, we just did the 20, so the mean is 0.4 times 5, or 50, which is 20. Now we are assuming that this is binomial, so we're going to use that formula from last time. It's the square root of the sample size times the probability of success times the probability of failure. How did I get to 0.6? It's because 0.4 and 0.6 have to add up to 1. And that turns out to be 3.46. That much. So this would be around 24. I'm going to round this 3.46 up to around 4. And this would be around 28. This might be 16, and this might be around 12. Since the standard deviation is 3.46, and like I said, after 2 standard deviations, you have very little data after that. So it should be no surprise then, number 6, what's the approximate shape of the sampling distribution for x? It will be approximately normal. There was one more thing though that we need to verify to say it's approximately normal. Since this comes from binomial, we need to know, are we expecting at least 10 successes and 10 failures? This is called the large counts condition. So when we found the mean, that was the number of successes we expected. The mean was 20. 20 is at least 10. So how we would document this is we would just say that since 0.4 times 50 is 20, that's greater than or equal to 10. For our failures, change it to 0.6 times 50, which would be 30, which is greater than or equal to 10. What happens is if you don't have at least 10 successes and 10 failures, then the binomial doesn't start to look normal. It will be skewed. And so this is good. We've got it. Alright, now what we're doing here is we're trying to develop a new formula for proportions. So you see how proportion of orange candies is bolded, and now I highlighted it. That's really what we're after, is what's the formula for proportions. So it says instead of finding the number of candies that are orange, we will now find the proportion of candies that are orange. Emphasis on the word proportion. So it says use your samples from number 2 and turn each number of orange candies into the proportion of orange candies in the sample. Write the proportions below and add them to the dot plot on the board. So if I take my first sample, which you remember was 16, it was 16 out of 50. So that's how I knew it was 0.32. So here's a really weird idea. We put that equal to P, and then we put this funny symbol on top of it called a hat. Well, that's really not a hat. That means it came from the sample. See, if we just use P, the letter P, that means it came from the population. And you probably, if you did the lesson the way it says to do it, you have 5 of these numbers. You just divide all of them by 50. So what it will do is, let's say on the right, this was our original dot plot. Okay, and I'm going to try to make it look a little bit normal with a peak and then coming down. Okay. If we take each of those points, remember this is centered around 20. If we divide everything by 50, what that's going to do is it's going to transform them into a smaller version. And the 20, since that's 0.4, that's going to be where the peak is. But the only question is, what's going to happen to the standard deviation? Wouldn't the standard deviation have to shrink if everything else is going to shrink? So we're going to get a little version of that right over here. Okay. Shrink. Oops, shrink. Can't spell anymore. Shrink by 1/50. Now, what does each dot represent? Well, now it represents the proportion of orange from a sample of 50. So it went from the absolute number to proportion. I guess you could use as a synonym for that. You could say the percent of orange that came from a sample of 50. Now, find the new mean and the standard deviation. Wouldn't that make sense if we just divided by 50, that the mean and the standard deviation would also get divided by 50? So if we use our previous answers, the mean was 20. Okay, and now this is going to be another funny way to write this. The mean sub p hat. The mean of the sample proportions is 0.4. What happens to the standard deviation? Well, that was the square root of 50 times 0.4. I'm just going to do parentheses. 50 times 0.4 times 0.6. But now that's got to get divided by 50. And if you do the calculation, it'll come out to 0.069. Well, with a little bit of algebra, you can take this and transform this into a slightly different formula. And we'll put this in the notes, but I'll write it over here. The standard deviation of the p-hats is going to be the square root of p 1 minus p over n. So that's an algebraic transformation. Okay, 11. What is the approximate shape of the sampling distribution for p hat? Explain and sketch below. If it started out normal, it's going to finish as normal, right? We're taking a normal graph, we're just dividing it by 50. All that's doing is compressing, and so it's going to stay the same. The shape will stay approximately normal, just squeezed into a smaller interval. You might be wondering why. Why did we do this? Why did we go from the absolute number to now a proportion? And really the reason is that's going to be the most useful for realistic problems about the world. See, we usually get information to us in the form of proportions rather than absolute numbers. Okay, now let's work on the last one, number 12. We know that bags of Reese's Pieces contain exactly 40% that are orange. If we select a random sample of 50 candies, what's the probability that the sample proportion will be 50% or greater? Okay, so notice the key percentages here. So it's a bag with 40% orange, and yet we're saying, what's the chance of getting 50% or greater? Doesn't that seem a lot like our simulation project, where you started with one proportion, say 40%, and then you saw, was it rare to ever get 50%? And remember, 5% was considered the standard for rareness. So let's think in terms of that when we get our answer to this. Is it rare to get 50%? And if it is rare, we'll say, that must be a special bag of Reese's. But if it's not rare, we'll just say, oh yeah, that's random sampling for you. That's expected variability. Now notice, we do need to know our sample size of 50 candies. But here's the neat thing. What's the population size? What's big N? Well, it's unknown. It's all Reese's Pieces that have ever been made. We don't need to know it because we're going to use the normal approximation. So that means we need to find the z-score. So the z-score would be, okay, the data value, which is 50%, minus the mean, which is 40%, divided by the standard deviation, which we did up here. Okay, it was 0.069. 1.45. So the mean would be at 0.4. I'm going to say it's normal, right? 0.5 is going to be about 1.45 standard deviations away. So I'm going to put it right here. Very not good graph, but basically we're looking for this area under the curve here. Not this. So I'm going to go on the internet and look up 1.45. Looks like it's about 0.9265. 0.9265. So we looked up 0.9265, and again, one moment. I'm getting a call from the principal.
Hi, Stats. We totally missed you.
Is that really what we wanted? Did we want 0.2965? No, we didn't, because again, the z-chart shows you the left side, but we want the right side. So that's why, like for example, when we're teaching AP, we say this is very important for you to keep straight what you're doing. So I'm just going to go 1 minus 0.9265, and then so it's really small. It's like less than 8%. So 1 minus that. Yeah, it's 0.0735, or about 7%. Big idea number one. When you're talking about, and notice the title here, by the way, the sampling distribution of p hat. So let me emphasize that since we weren't in class for the video. A sampling distribution is when you take a bunch of samples of the same size and you put them on a graph together. Some will be small, some will be big, but the idea is that the mean of that sampling distribution will approximate the mean of the whole population. And that's really a breakthrough as far as stats goes. And of course the standard deviation, we can get the formula from that as well. So I guess number one would be, oops, writing in highlighter. What do I always say about that? Mean and standard deviation. Mean and SD. That the mean of p hat is p. Now that means the mean is the same as the mean of the entire distribution. So if you do a sampling distribution and you find the mean, you've just found the mean of the whole population. That's great. So let me write that. The standard deviation of p hat is the square root of p 1 minus p over n. Now when you're doing that in a calculator, because the square root covers the entire expression, either use parentheses or make sure that you press the equal sign after you've calculated this part. You need to get that expression and then take the square root of it. Okay, second big idea, large counts. Okay, ensures normality. NP has got to be greater than or equal to 10, and so does, n1 minus p, greater than or equal to 10. So that means that the number of successes we expect is at least 10, and the number of failures we expect is at least 10. The reason I keep saying we expect is because you might actually get fewer than 10 on any one sample, but we expect in the long run to get at least 10. Okay, and the last one, number 3. If we take the process of this last problem up here, let's see, if we go through here and we take number 12 and we turn it into a single formula, what it would look like. The probability, if sampling distribution of p hat is normal, you can get the z-score from doing p hat minus p over the square root of p 1 minus p over n. In other words, you're taking this formula and you're sticking it down here in the bottom of the equation. And then the top of the formula, this is what we would always call in class data minus mean. Data minus. So I actually don't like to use this formula. That's one more thing to memorize. If you're going to memorize something, memorize everything that's in big important idea number 1.